a changing current. Is it increasing or decreasing?
Holy shit.
Decreasing.
Decreasing, right? You always start with the maximum current because this thing has the maximum voltage, and as it discharges, the current decreases. If it's decreasing current, what does this thing try to do?
Power itself. Power.
Push the current in the same direction. So it tries to boost the current, and that gives you just enough to charge the capacitor in the reversed orientation. So if you start with positive charges up here, you end up with positive charges down here. But now you'll have a charged capacitor again. Okay? So the current goes this way. And then when it gets to this thing, it's decreasing, so this thing boosts it until it charges the capacitor the other way. And so you can see, what kind of motion is this? Kind of
Like an AC?
Kind of, yeah. So this is like periodic. Okay? So, here it is in snapshots. So you start with a charged capacitor, okay? This has an initial charge, let's say Q naught. Alright, so we close the switch. This thing starts to discharge, okay? As it's completely discharged, that means so this has a maximum charge, this ends up having a maximum current when this is totally discharged, okay? Then it recharges the capacitor, and the whole thing starts over, okay?
Just backwards, right?
Yeah, so back and forth. This is the whole cycle, and then you end up back where you started. And so this is some sort of periodic motion, okay? So you'll end up with some sort of differential equation that looks like the one for the spring, and it goes back and forth. So that means it has a frequency and a period, and you can plot it as a sine wave, all right? So if you want to look at that, that's what it looks like. And these letters actually correspond to those stages that we were talking about. So this is the charge. This is when your capacitor is totally charged, right? And remember, what's current? Because this is Q. How do you get current if you have Q?
Charge over time.
dq dt. So what do you think the current graph looks like here? What's the derivative of this thing? It's flat. That means it's 0. Okay. Where's your maximum current going to be? At B or at D or at B, right? And then they're going to change sign because the slope's changing sign. So here's your induced current. Okay. And we can tell because this is a sinusoidal graph, we're going to have a frequency. And it turns out the frequency is 1 over the square root of inductance, L, times capacitance, C. Okay? So an LC circuit has a frequency. Now this isn't just a frequency, this is an angular frequency because it's 2 pi times the frequency in radians per second. Okay? So that's an LC frequency. And there's a whole differential equation that goes with this. I just want you to know that there's a differential equation that leads to the sine and cosine. How do you think you get the differential equation? Loop law. Okay? Remember, what's delta V for a capacitor? Got a Q and a C somewhere.
Q over. No,
So-
it's QC. No?
So remember, C.
C equals Q over V, so you multiply by.
Okay, so yeah, it's Q over C.
Q over C.
And we also said delta V for an inductor.
I'm fucking starving.
What's that going to be?
L di over dt.
Okay. So this ends up being the second derivative of Q, right? Because I is dq dt. So you can rewrite this as negative L d squared Q dt squared. Now you end up with this plus this equals 0, right? This ends up being positive just because of the way that you're going around the loop. So you end up with a differential equation with a second order differential and just a variable and then a negative sign. And that looks just like the spring, right? Then you have negative kx equals ma A is the second derivative of x with respect to time, it gives you the exact same solution. Okay, so when you do have to know some differential equations for physics. A lot of them are the same differential equations, so you only really need to know like 5-ish solutions to differential equations, which if you don't like differential equations, that's pretty easy to remember 5 things. So just
You'd be
memorize those
surprised.
5. Or write them down. But anyway,
No cards.
you end up with this cyclical process, and it looks like this. Okay? So, how do you get the frequency?
Yeah, that.
1 over square root of
Yeah, that.
LC. Cool. Try it out.
Fuck.
Do you remember how to add? Okay. Let's discuss Will again. Better. Okay, so let's walk through this. So frequency is 1,000 hertz. Okay? So couple things. We know omega is 1 over square root of LC. Okay? What kind of frequency is that? Is that in hertz? What are the units of omega? Radians per second. Okay, so frequency is equal to 2 pi over square root of LC, which isn't going to end up mattering, but it's important to remember that in the frequency and frequency you're off by a factor of 2 pi. Okay? So our initial frequency is this. Our later frequency is going to be 2 pi over square root of L times C equivalent. Okay? How do we add up these capacitors? Yeah, 1 over C plus 1 over C inverse. Okay, so you get 2 over C, that gives you C over 2, so 1/2 C. Okay? So that gives you C, and then there's a 1/2. Okay? You pull this out, and you end up with square root of 2 pi over LC. But what is this? That is frequency 1. Okay? So you get square root 2 times frequency 1. Frequency 1 is 1,000. Square root of 2 is 1.41. Okay? So that means you have square root of 2, 1.41 times 1,000. That should be D. Okay? Alright. So it depends on 2 things. If you remember how to add up capacitors in series, and then just a ratio. Okay? Alright, any questions about that? Cool. So what are some uses for LC circuits?
LEDs, we have like blue, red,
Well, you could, yeah. It's like some sort of cool strobe light, I guess. Yeah. Yeah, anything with a frequency. What else has frequencies?
radio.
Radios, cell phones. There's an LC circuit in here. And then we have this very dated picture of cell phones. But to be fair, they still use LC circuits. So what else uses LC circuits? Even older technology. Radios, okay? So these all have a resonant frequency. So if you are listening to a radio station, how do you change the you change the frequency. So there's, well, yes, AM is amplitude modulated. So basically you have a sine wave, and then you encode the information onto the sine wave by either adding sine waves that modulate the amplitude or adding sine waves that modulate the frequency. So those are the 2 types of radio waves that we deal with. Yes.
Not to get sidetracked, but when it comes to radio waves and stuff like that, what is a carrier wave? Is that like the same thing? Like
The carrier wave is the frequency you tune to, okay? And then the information is embedded in the carrier wave, right? So it's like you add a bunch of smaller waves onto the carrier wave, and then you read those waves at the other end.
so they're less than the frequency you tune to?
They're smaller. So like it would be like a smaller amplitude and smaller frequencies that you can sort of put into the main frequency. So basically your strongest one, and then you put smaller ones on that you can read later. Okay, so it's smaller. It's kind of like a fuzzy hand-wavy explanation, but that's the basic idea, right? You have this main wave that you use, that you transmit at that frequency, and you receive at that frequency, and then all the other frequencies that are off resonance, those are what you read as the information. So you can put your sound waves on top of your carrier wave, and that's what you read as music on the other end. All right. So basically, what you have when you broadcast from a radio station is a tower that has an LC circuit and a lot of power, and that generates the wave that goes out. Okay, and then at the other end, your radio has a tunable LC circuit. So either you have a variable capacitor or a variable. Usually, I think you move along the inductor coil, so you have like a coil, and you can move where the other end of your circuit is, so that you can tune to a particular frequency, right? By just changing the inductance, and then you can receive different radio stations from all the different broadcasts. Okay. The technology you use in a cell phone is a little bit more complicated because you can jump around on different frequencies and the cell towers, and it's all like it's a lot harder to understand. But it's the same basic idea. It's just the computation of how you use it is a little bit different. And so this thing has a lot more complicated circuit in it than a radio. Like you can build a radio broadcasting station and a tunable radio pretty easily. Like back when, is Radio Shack still a thing?
No.
You can still get the parts, right? I mean, honestly, an inductor, how do you make an inductor?
Coils in it.
Yeah, you just need wire, okay? You just coil the wire. The density of the coils gives you your inductance, so you can just sort of make that yourself. It's pretty easy. And then capacitors are pretty cheap and easy to buy. We've got like a crap load in the back. For like $20, you can get like all different sizes of capacitors and like hundreds of them, okay? So making a radio receiver, really easy. It's like something you could MacGyver in an emergency, no problem, okay? And then all you have to do is attach it to a speaker. And what's a speaker?
Big magnet.
It's basically just a magnet, some wires, and another coil of wire and some cardboard, okay? Like to make a really basic speaker. So you can build a radio for like under $10, okay? Which is good to know if there's ever like an apocalypse and there are any people still broadcasting. If you find yourself in a Walking Dead situation, obviously there'll be a bunch of abandoned cars and you can just use their radios, but you could easily make a radio if you had to, okay? And the way that you would figure, so let's say you want to get so when you listen to AM 1070, what's the 1070? What units is it in? Hertz, okay? And so if you want to figure out how to build something that has 1070 hertz, you can, okay? Because obviously this is in radians per second, so you have to convert it to hertz, so you just divide it by 2 pi, but this can get you 1070 hertz, so you just keep coiling your wire and calculating your inductance until you get the right one, because probably you have a capacitor that's got a fixed value, so you just have to create the right inductor, okay? It's really shockingly simple, and that's technology we've known about for 200 years? Yeah, 200-ish years, okay? Maybe longer. So, not gonna do that math in my head, but let's try a problem, okay? So let's say we have a 1 millihenry, right? That H is for Henry. And what are henries a unit of? Inductance, okay? So we have a 1 millihenry inductor. We want to know what capacitor should we choose to make an oscillator with frequency 920 kilohertz, okay? And this is basically the problem I was just describing. Let's say we want to tune into AM 920. What do we have to use?
Okay, so here we're given an inductor, and we want to know what capacitor we're going to need in order to reach a particular resonant frequency. So we know that omega equals 1 over the square root of LC. So solving for C, we get omega squared is equal to 1 over LC, and therefore C is going to be equal to 1 over omega squared L. Now we have to go in and find our values. So we have this 1 millihenry inductor, so that's this, and we have this frequency. Now this frequency is not omega, this is F, and so that's going to be 920 times 10 to the third hertz. We have to remember back from our angular stuff in Physics 190 that omega is equal to 2 pi times the frequency. So really, when we want to write this out, if we don't want to have to convert, this is going to be equal to 1 over 2 pi frequency squared L. All right. So that, remember this frequency F, this is not the same as omega, okay? So in order to get omega, we have to convert. Okay, so now we can plug in our numbers. This becomes 1 over 2 pi 920 times 10 to the third hertz. We square the whole thing, and this is 1 times 10 to the negative third henries. Now it turns out a henry divided by second squared is inverse is going to give you something in farads. That's kind of hard to deal with, but let's just plug in the numbers, and we get 3 times 10 to the negative 11th farads, or you could call this 30 picofarads. So what does this give us? Well, this means if you have a capacitor of 30 picofarads, okay, 30 picofarad capacitor, and a 1 millihenry inductor, you can now tune in to AM 920 or whatever, okay?